All right, guys, what we're doing today is starting Chapter 7. Chapter 7 is going to be systems of equations and some rational expressions. So the first thing we're looking at is systems of equations, specifically linear and nonlinear systems. So linear and nonlinear systems, we're looking for the point or points that's going to make both equations true. Now, the first method that we have for solving a system of linear and nonlinear equations is substitution. Most problems involve either a function of one variable or a single equation in two. However, many problems have more than two. So with substitution, we're going to be given two equations. We're going to substitute one into the other. We're going to find a value substituted in. Now, a solution of this system is an ordered pair that satisfies each equation, makes both equations true. So, for instance, the ordered pair 2, 1 is a solution. So if we take the point 2, 1 and plug it back in for x and y, we get 2 times 2 plus 1. 4 plus 1 equals 5, so yes. So this is true, so it works for the first equation. We can use 2, 1 for the second equation, plug in 2 in for x, 1 in for y and solve, and yes. Just like the first one, we do get 5 equals 5. Here we do get 4 is equal to 4. So it works. It's a solution. With systems, it's got to work in both equations. So to solve by substitution, we solve one of the equations for one variable in terms of the other, substitute it in, solve, and then find the original, or find the other one. So if we look at these two equations here, x plus y equals 4 and x minus y equals 2. So we could pick one of the two equations, either 1 or 2, and get one of the variables by itself. So let's just take the second equation, x minus y is equal to 2. Now we could solve this equation for x or y. I'm going to solve this for x. We can add y to both sides, telling us x is equal to y plus 2. We need to get one of the two variables by itself because it's telling us that x is equal to y plus 2. At this point here, we can substitute the y plus 2 into the other equation for x, giving us y plus 2 plus y is equal to 4. Now we just need to solve this equation for y. So we can simplify or drop our parentheses. Combine like terms, our y plus y gives us 2y. Plus 2 is equal to 4. At this point here, we can subtract 2 from both sides, telling us 2y is equal to 2. Divide by 2, telling us y is equal to 1. Now at this point here, we just need to solve for x. So we can take the equation that we used for the substitution, that x is equal to y plus 2, and plug our value of y back in, telling us that x is equal to 1 plus 2, or x is equal to 3. Thus meaning that the point 3, 1 is our solution for this system of equation. It's the point that's going to make both of these equations true. And if we wanted to check it, all we had to do was take the point 3, 1 and plug it back in. And in the top equation, we'd have 3 plus 1 is equal to 4. Well, yes, 4 is equal to 4. And in the bottom equation, we'd have 3 minus 1 is equal to 2. Well, 2 is equal to 2, telling us that the point 3, 1 is the solution for the system of equations. Questions on this here? All right. Now for them, they solved it by getting one of the equation y by itself. They picked the top one, y is equal to 4 minus x. Substituted into the other equation, telling us that x is 3. We found y first, then found that x is 3. And when they plug the value of x back in, we get y is 1. And when we check, we do see that both of those work. So the 0.31 is our solution. I think y'all remember doing these. It's been a minute because we did this in Algebra 1. Questions on solving by substitution? Do you feel comfortable with this? Okay. Now the term back substitution implies you work backwards. So we solve for one variable and then work backwards. All right. Let's look at nonlinear systems of equations. Now nonlinear systems of equations could mean a lot of different things. But for the main thing is that at least one of the two equations isn't aligned. That's all it's saying. So we can still use substitution. So we have this equation here. 3x squared plus 4x minus y is equal to 7. And 2x minus y equals negative 1. We have two options to go with this here. We either get x by itself in one of the two equations or get y by itself. Now, if we get x by itself, especially in the first equation, we have two different terms for x. It's going to be a little bit harder to get it by itself. So what we could do is we can take the bottom equation, 2x minus y equals negative 1. Solve it for y so we can plug it back in this place here. Because if we solve this for y, minus 2x from both sides, it's going to tell us that negative y is equal to negative 2x minus 1. But we don't want to know what negative y is. We want to know what positive y is, yes? So what would positive y equal? Yeah. I changed y's value. I changed the sign on one side. I have to change the sign on the other. Or mathematically, we could say that I multiply through by negative 1. I'll put parentheses around that. Negative 1 times negative y is y. Negative 1 times negative 2x is positive 2x. And negative 1 times negative 1 is positive 1. Now what we're going to do is take this and replace every y in the first equation with 2x plus 1. So that'll give us 3x squared plus 4x minus 2x plus 1 is equal to 7. At this point here, we can distribute that negative through here, giving us negative 2x minus 1. Combine like terms. And we don't need that second parenthesis anymore. Plus 2x minus 1 is equal to 7. Questions on what we've done so far? Now we do have a quadratic. And the reason we have a quadratic is because we have that x squared term. Whenever we have these quadratic equations, the x squared term, and we do have an x term, what did we have to do with this equation? We had to get it equal to 0. Giving us 3x squared plus 2x minus 8 is equal to 0. And we can factor. Because when we solve quadratic equations, we had many different ways to do it. We had the square root method, and that does not work nicely here. It could, but we would need a single set of parentheses. We can factor it, graph it, or quadratic formula. Now, graphing, there's a good chance, not a good chance, it will give us one of the two if we graph this. If we grab the graphing calculator and graphed it, it would give us one of the two. But because of the 3 in front of the x squared, it means one of the factors, one of our solutions, is going to be rational. Since the third term is negative, our signs are opposite. Only factors of x squared are going to be x and x. And we'll have 3 and 1 for our 3. We can put it in the first space or the second. Only factors of 8 or 1 and 8, or 2 and 4. So we'll do 4 and 2. And if we check this here, 3x times negative 2 would be negative 6x. 4 times x would give us positive 4x, giving us a middle term of negative 2x. Correct number, but wrong sign, so we need to flip the signs. So our two factors for this here are 3x minus 4 and x plus 2. And again, at this point here, zero product property. Anytime we have two or more things multiplied together to equal 0, one of them is going to have to be 0. Add 4 to both sides, telling us 3x is equal to 4. Divide by 3, telling us x is 4/3. On the other side, we can subtract 2 from both sides. Minus x is equal to negative 2. Questions on how we got our two values of x? Now at this point here, we got to plug them back in to find the value of y. So we can start with 4/3. So it's telling us y is equal to 2 times 4/3 plus 1. Now our 2 times 4/3 would be 8/3. And 8/3 plus 1 is going to be 11/3, telling us that this solution is the point 4/3 comma 11/3. We'll do the same thing for negative 2. Y is equal to 2 times negative 2 plus 1. Y is equal to negative 4 plus 1, so y is negative 3. And that is the interesting thing with these nonlinear systems of equations. We don't have just a point. We can actually have 2 points that work with this here. Because what we have with this is the first one's a quadratic, a U-shaped graph, and the second one's linear. So we do have these 2 points where it crosses. It is possible to have a quadratic in a linear equation and only have it intersect at 1 point, no points, or 2. Questions on this here? Four thirds negative 2, 4/3 comma 11/3, and negative 2 negative 3. Questions on how we did this here? We can look at another one of these here. Now again, I would solve this equation here, the non-quadratic, the one that doesn't have the x squared, for y. Because we could solve it for x, but if we solve this equation for x, we do have to put it in both of the x terms. Now, if we did that for this here, you don't have to write this. We'd have, no, x is equal to negative y plus 5 over 2, which would flip our signs, y minus 5 over 2. And we'd have to plug it back in, giving us y minus 5 over 2 squared minus y plus 3 times y minus 5 over 2. And I would say solving it this way is not so much the fact that it's a fraction, it's the fact that we're having to square one of these two terms. So it's more to do, more process, more work, where if we solve this equation for y, add 2x to both sides, we get y is equal to 2x plus 5. We don't have a fraction, which is nice. And when we take this and replace every y in the second equation with it, we get x squared minus 2x plus 5 plus 3x is equal to 1. We don't have any of these expressions being squared. I'm not having to plug it into y squared. And it's not that it makes it harder or more challenging, it just makes it a little more tedious. We don't have to square anything this way. Now at this point here, we can distribute the negative. Combine like terms. Negative 2x plus 3x is going to be plus x. Get everything on the same side of the equation, telling us that x squared plus x minus 6 is equal to 0. Question on how we got here. Now at this point here, there's not a number in front of x squared, so we can actually graph this and not have to worry about any fractional answers. X squared plus x minus 6 gives us this here. And if we go second graph, we see that the values of x that make the y 0 are negative 3 and 2. So it tells us that the solutions for this here is that x is equal to negative 3 comma 2. And the last thing we've got to do is plug it back in. Y is equal to 2 times negative 3 plus 5. 2 times negative 3 would be negative 6. Negative 6 plus 5 is negative 1. So negative 3 comma negative 1 is our first solution point. We can do the same thing with 2. 2 times 2 gives us 4. 4 plus 5 is 9. So the point 2, 9 is our other solution point. Questions on this here? Now let's say we wanted to graph this. Now to graph it, we would have to get y by itself. Now the top equation, we already did that. We did that as part of our solution for this last one. Now we can get this quadratic equation with y by itself, but we have to just move a few things. One thing we'd have to do is add y to both sides. And we'd also need to subtract 1, because our negative y plus y would be 0. Our 1 minus 1 would be 0, telling us that y is equal to x squared plus 3x minus 1. And now that we have them both as y equals, we can come over to the graphing calculator. Say 2x plus 5. I got that right. Yep, 2x plus 5, x squared plus 3x minus 1. X squared plus 3x minus 1. And we can tell the graphing calculator to graph this here. And again, we're looking for intersections. We're looking for where they cross. Yes, I did. That would make a big difference. There we go. Now we can see that it does cross in two places. If we look at the table, we're looking for what values of x will make the y values be the same. Well, at negative 3, the y values are both negative 1. So the point negative 3, negative 1 is a solution. And the other one is at 2, 9. So 2, 9 is our other solution. Questions on this here. Now we can have the calculator tell us this, so we can go second calculate. And the fifth one down is intersect. Now to have it do this, if it only intersects at one point, you could just hit enter 3 times. Enter for the first curve, enter for the second, and then enter, and it will tell us the solution. But here, there's 2 points of intersection. So the first thing we need to do for the first curve is using the left and right arrows only, move it so it's very close to where they cross. And we hit enter. And what we've told the calculator is somewhere near that X on that blue line, there's a point of intersection. And now the one for the red is also very close to it, so we can hit enter. Now it's asking us, do we want to take a guess at what the X and Y values are? No, I don't feel like guessing. Hit it a third time, and it tells us that the intersection where they cross is at 2, 9. That's our point. Now we can do it again. Second trace intersection. But this time, we're going to move it over here so it's close to the other intersection. So I hit enter for the first one. If you notice, the second curve, it moved that X over close to it. Enter one more time, and it tells us the intersection is -3, -1. And that's it. Questions on this here? Graphing, a system of equations, we can graph to find the intersection. Now, some of the homework problems, it'll tell you to solve it by substitution and check your solutions with graphing. It'll give you the graph. And all that's saying is, do the solutions you got from using substitution match the graph? That's all it's saying. Or you can just use the graph to check it. Because here we see that the 2 lines cross at 2, 0. Here, they cross at these 2 points. In this last one, there is no intersection. And since they do not cross at all, there are no solutions. So if we want to solve this system of equations, y equals the natural log of x, and x plus y equals 1, well, both equations need to be in y equals form. Well, the first one's fine. The second one, I need to subtract x from both sides, telling us y equals -x plus 1. At this point here, we can type these in. So we can grab the graphing calculator, hit y equals. And the first one we have is the natural log of x, -x plus 1. Graph. So we have these 2 graphs, and there is a specific spot that they cross. Now we can look at the table, and we're looking for where the y's are the same. Well, at 1, the y values are both 0. It tells me that the point of intersection, or the point that these 2 are both the same, is at the point 1, 0. And that's it. Because when we graph these, we see where they are the same as at 1, 0. And if we check the solution, 0 equals the natural log of 1. Well, the natural log of 1 is 0. So 0 is indeed equal to 0. Plug 0 and 1 into our other equation, and it works too. Example 5 shows the benefit of graphical approach to solving systems of equations in 2 variables. Notice that by trying only the substitution method in example 5, would obtain the equation x plus the natural log of x equals 1. It would be difficult to solve this equation using x by standard algebraic techniques. So it's a little harder for that one there. And it's even true for this here. Now the first one, y is by itself. The second one, we could get y by itself, telling us y is equal to 2x plus 1, 3 minus log of x, 3 minus log of x, And I think the other one was what, 2x plus 1 graph. Now again, we do have a nice intersection. Now for this one here, we'll go second trace intersection. And the intersection for this here is the point 1, 3. Now, since there was only one intersection, really we just needed the x to show up on both lines, and it's going to find the only intersection point. 1, 3. Questions on this here? That's it.